Hello and welcome to this video. Now in this video, I'm going to talk about current measurement using Arduino. So for current measurement, we have these current sensors available. So the first one in the right side that you can see is the INA219 current sensor. So it measures the voltage drop across the shunt resistance to measure the current that is flowing between the circuit. The advantage of this INA219 is that it's quite easy to implement in circuit. We have a dedicated library from Adafruit that can handle all the necessary parameters to get the job done. Another advantage of this sensor is that this chip can actually measure the bus voltage using these two other pins. So you can connect the Vin minus to the ground and Vin plus to the positive voltage to measure the voltage also. But this sensor can be used only to measure currents up to 3.2 amps maximum. So the other options that we have is these two sensors. Now, obviously the one with the big chunky connectors is obviously for higher currents. And in the left side, we have lower current versions. In the left side, I have the ACS712. And in the right side, in the middle, I have the ACS758. So this smaller one comes in three variants: 5 amp, 20 amp, and 30 amp. So this one is the 30 amp version. Then the ACS758 is actually the bigger brother of this ACS712, which has also the same Hall effect sensor inside that measures the magnetic effect of current when the current flows through the conductor. So these are basically analog sensors, which gives us analog voltage data into the output pin of the sensors. So using the Arduino's internal ADC, we can measure the analog voltage that is coming out of these Vout pins, and then we can convert that to the current value. Now in this video, my main focus will be to use this middle sensor, that is the ACS758, because you will find a lot of videos on using this ACS712 modules in YouTube and this INA219 as well. So I'm not going to discuss about these. Rather, I will be discussing only about using this ACS758. So now if I look into the datasheet of this ACS758, the first page obviously gives us the features and benefit and the description of the sensor. The output of the device has a positive slope greater than VCC by 2. So that means when there is no current flowing through the sensor, at that moment, we will be getting VCC by 2 volt. So if you are running this at 5 volt, you will be getting 2.5 volt out of the Vout pin of the sensor when no current is flowing. Then we have the typical application circuit diagram here that uses this one capacitor and another capacitor between the ground and VCC. So these two capacitors are to reduce the amount of noise. Then in the next page, we have the variant information. So various variants are available of this ACS758. That is, we have the 50 amp bidirectional version, then 50 amp unidirectional, then we have 100 amp bidirectional and unidirectional. Then we have 150 amp bidirectional as well as unidirectional. And then also we have the 200 amp unidirectional as well as bidirectional. So we have a huge room for measuring current, but obviously that comes with a trade-off in the sensitivity. So as you go on increasing the current measurement capability of the sensors, you actually lose sensitivity of the sensors. So you can see here, the 50 amp bidirectional has the sensitivity of around 40 millivolt per amp, whereas the unidirectional one has 60 millivolt per amp. Then we have same for the 100 amp bidirectional as well as unidirectional one. The bidirectional one has the sensitivity of 20 millivolt per amp, and for the unidirectional, we have 40 millivolt per amp. Then for the 150 amp and 200 amp, also you can see the value actually decreases as we go on increasing the current measurement capabilities. So here in the operating characteristic, we have the VCC that can take from 3 volts to 5.5 volts, and typically it is ideal for 5 volt operation. And that is what we are going to do using the 5-volt Arduino only. Then we have another important parameter to note here is the amount of noise that it is going to generate. So you can see here the 50 amp bidirectional one has a noise of around 10 millivolt at 25 degrees Celsius and 10 nanofarad on V out and ground pin. So if you connect this capacitor to V out and ground, even then you can get a noise of around 10 millivolt. So now this value actually depends on the test condition. So now I have made a very simple circuit to measure the current flowing through this sensor when I light up this light bulb using a 12-volt supply. And this output of this sensor is connected to my self-made Arduino that I will be using to read the current measured values. Now let's get back to the software part for measurement. Here I have written a very simple sketch to measure the current and the analog values. So the code is pretty much self-explanatory. The first is to define the connected pin. Here I am connecting to A2, the analog 2 pin of Arduino. Then I have declared some floating variables and then serial begin, then some serial print. And here in this line, I will be calculating the current. So first current raw will measure the analog read of the connected device, that is our current sensor. So this variable will store the analog value or the ADC value that we are reading from the sensor. Then to calculate the current value, we will subtract that with 508. Now this 508 actually comes from the concept that Arduino has a 10-bit ADC. That means the ADC value can range from 0 to 1023. And if you divide those values by 2, the half of those values will be 512. Now, this 512 is actually the ideal value to get 0 volts because this sensor is bidirectional. So it is giving the halfway between the 0 and the 5 volt. So it is giving out 2.5 volt, which is equivalent to 512 in the ideal condition. But since I'm using the USB power, which is not at all regulated to give exact 5 volt. So there is little drop in the reference voltage. So we are getting almost 4.9 volts or so. So due to that fact, we cannot use exact 512. Now, if you are using a constant 5 volt supply, then obviously you can change this to 512. So that depends on the reference voltage that you are using. Then we will multiply this with 4.88, which is the ADC sensitivity of Arduino analog pins, and divided by the sensitivity value, which is 40 in case we are using this 50 amp bidirectional version, as we have seen in the datasheet as well. The bidirectional ACS758 has a sensitivity of 40 millivolt per amp. So that is why we have used this 40. So using this code, I will be first printing the ADC value, and then I will be printing the calculated current using this line of code. So now I will compile and upload the code and see what happens. So here we are measuring 508 or 509, that is our current value is 0. So that means now there is no current flowing through this, and still sometimes when the value changes, as you can see here, when it is 510, we are getting a noise of 0.24 or 240 milliamps of noise. When this is exact 508, we are getting 0. When this is again 509, we are getting 120 milliamp of noise. So now I will turn on the light bulb and see how much current it is drawing. In the multimeter here, I have set this to current measurement so that we can verify the measured value. So now that I have turned on the light, here I can see in the multimeter it is reading 2.13 around volt. And we are reading here in the computer screen in our serial monitor 2.32 or 2.2. So that means we are getting around 120 milliamp and sometimes 240 milliamp of noise in the circuit because of the flowing current. So as you can see nearby, I'm using the computer and all these equipments to record the video. So all these things actually contribute to some sort of noise into this current sensor. So now that we have seen how to measure the current directly from this current sensor, but the resolution is obviously up to 120 milliamps. And if there is a slight noise in the readings, we will get a precision of around 120 to 240 milliamps. Now, if we want to increase the precision of measurement, because we cannot measure any current which is below 120 milliamp or which is not in the multiple of 120 milliamps, because one bit or one ADC value can only measure 120 milliamps in a 10-bit ADC. So what if we want to measure current with a more precision or more precisely, we can how we can measure the current? Then the solution to that is by using an external ADC converter. So here I have this little module, which is the ADS1115, which is a 16-bit ADC converter. So now I'm going to use this 16-bit external ADC with Arduino to read the sensor values, and we will see whether we can get more precise measurement or not. So now if we take a look into the datasheet of this ADS1115 ADC converter, in the first page we can see here the measurement that it can take using the internal programmable gain amplifier is between 256 millivolt to plus or minus 6.144 volts. So that is the range that we can set using the internal programmable gain amplifier. Now, by default, it is set to measure between minus 6.144 to plus 6.144. And the reason is that if you set this to lower values, suppose you set it to measure between plus and minus 4 volts, and if you are using a 5-volt analog supply, that analog value, if it exceeds the set gain amplifier, then there is a chance that you might destroy the chip. So be careful. If you are using some circuits that uses the 5-volt rail or the 5-volt analog signal, then don't change the gain amplifier settings. Now, if we scroll down to the page number 6 here, we can see the recommended operating conditions. So here we can see the minimum and the maximum power voltage that we can give. So here it reads about a minimum of 2 to 5.5 volts. But even then, since the full scale range is between plus or minus 0.256 to plus or minus 6.144 volt, you can actually supply a voltage up to 7 volts to this chip. And now if we look into the full scale range and corresponding LSB size, we can see here when we are using the full scale range of 6.144 volts, then we are getting a resolution of up to 187.5 microvolts. So that is the lowest voltage that we can measure if we have the programmable gain amplifier set to measure between plus and minus 6.144 volt. So that is obviously quite a good precision in our case to measure the current value. Now in the datasheet of ACS758, if you remember, we have a resolution of 40 millivolt per amp. That means this 40 milliamp could be measured with a small steps of 187.5 microvolts. That 40 millivolt will be divided by this 187.5 microvolts, and we will get a value of around 213. So that means for every 1 ampere of current, we will have 213 ADC values, which further implies that 1 ampere can be divided into 213 parts, and we can have a resolution of up to 4.6 milliamps, because 1 divided by 213 will be approximately 4.6 milliamp. So we are going to use this value in milliamps to calculate our current reading, and we will definitely be using this range. So here I have made a very simple circuit to measure the current from this ACS758, and the analog value will be fed to the A0 pin of this ADS1115 ADC converter. Now this chip will convert the analog value to digital value, and it will send to the Arduino via the I2C bus. So now let's go to the software part to write a simple sketch to measure the current. So here in the computer screen here, I have written a very simple sketch using the Adafruit ADS1X15 library. So I have declared the model that I am using. In this case, I am using the ADS1115. You can use this for ADS1015 also. So you have to declare which model you are using in this line of code. Then I have declared a few variables. I have declared here a 16-bit integer ADC value because this ADC value will be measuring the ADC value that is measured by the analog input of the ADC converter. So that would be in this case our 16-bit number. But if we only declare int integer, it's actually a 8-bit in Arduino. So that is why I have declared it 16-bit. Then we have float, volts, and float sensitivity. Now this sensitivity is same in the previous code as well, because we are using the same current sensor which has the sensitivity of 40 millivolts per amp. Then in the setup section, it is very much the same, only we have this ADS begin function because we are using the ADS library or the ADS1115 library. And then in the loop, I am using this variable ADC0 to read the ADC values that is received into the chip using this function ads.readADC underscore single ended. And the 0 signifies that I'm reading the value from pin 0 of this chip. Now this chip has 4 input pins. Out of those 4, I'm using the A0 to read the value. So that is why it is written A0. Now volts 0, the float variable, will actually calculate the voltage or the analog voltage that is received from this current sensor. And in the next line, I will be calculating this current value using this line of code. So current equals ADC 0. Obviously, this is the ADC reading, and 13,333 is the mid value that we will get when we connect this to 5-volt supply. Now, if you want to read more about how we are getting this 13,033, you can go to my website and read the entire blog. I have written a detailed blog on this. You can read that. I will put a link in the description to my website. You can download the codes, you can download the schematics and everything. So make sure to check the description for the link to my website. So using this line, I will be calculating the current, and then I will be printing the ADC value, and then the volts, that is the analog voltage that is being received, and the calculated current value. So let's compile the sketch, and then I will upload and see what happens. And here we have in the serial monitor, we are getting the current ADC value and the analog voltage that we are reading. So now what I have to do is to adjust this value, that is our set 0 value, from 13,333, which is the ideal value when we put 5 volt into the chip. As in the previous case, we have not put 512, and instead we have put 508. So here also we have to adjust this value. Now, how I can adjust, here you can see after uploading this sketch, I can read a analog value of around 13,135, 48, and 37, like this. So in between these values, I will be setting this to 13,145. So let's set this, and then I will upload this sketch, and I hope I will be getting values more near to 0 amp. So now in the serial monitor, we are getting 0 amps sometimes, and sometimes 30 milliamps, 20 milliamps. So now this is the no load current, and now let's turn on the light bulb, and I will see what is the current measurement, and I will verify that using the multimeter that is connected in series. So here I have turned on the light, and now you can see it is reading 2.03 to 2.04 amps. And in the multimeter, we are getting around 2.1 amp. But still, I'm getting a very close value, and I'm getting a more precise value because of this 16-bit ADC. So this is how you can measure the current using a 16-bit external ADC. So I hope this video is helpful for you and you have learned something new. If you find this video helpful, make sure to like and subscribe to this channel. I will be posting videos like this. If you want to download the code and read more about these values and how we calculate these values, you can read them from my website. There is a link in the description to my website. Thanks for watching.